Hello again. So in this chapter, we have been spending a lot of time looking at ionic compounds and ionic bonding and the naming and the properties and learning about those new polyatomic ions, which are really important. But this chapter will also deal with metallic bonding, and there really isn't a large category of compounds that are called metallic compounds. We sort of call those alloys. And are they compounds or are they just mixtures? That's an interesting question. It could sort of go both ways. So we're just going to spend this one video talking about the ins and outs of what is going on in a metal. So how metals are, bonded together. If I have a hunk of lead, those atoms of lead are a metal, and they are somehow held together. And so what is holding them together? Well, that would be a metallic bond. Metallic bond is basically the bond that holds metals together. What is going on with them, with the electrons? That's really what we want to know. And metallic bonds occur when atoms of course, metals, right? Well, they give up their valence electrons. So very similar to ionic compounds in that they give up their valence electrons, but the electrons don't go to something else. They sort of exist in what we call the electron sea. What that you'll see in the pictures, it's sort of free-floating electrons that kind of hop between one atom and another atom and another atom. So now, what remains, if the valence electrons leave, then we would have positively charged metal ions, and these ions are now bonded through their attraction to those negatively charged electrons. Right? So if we think about what is going on in this picture, if this was, let's say, a diagram of iron, right? Then what these might be is iron 2+ ions. And then all of these would be these free-floating valence electrons all around it. And it's this attraction between those negative electrons and what remains after those valence electron leaves that holds a metal together. And this is what we call the electron sea. This is just another picture showing sort of the exact same thing, that we have this metal ion, and they call that's the nucleus, and the core electrons, right? Because the valence electrons have left. And now these valence electrons sort of hop from one atom to another atom. We sometimes call them, this is your sea of mobile valence electrons. Another word for that could be delocalized. We will use that word again next chapter when talking about certain type of electrons, but delocalized literally means not localized. It means that they don't simply stay with one atom. They move from atom to atom or from ion to ion. So that is kind of what is the bonding that's going on. Because metals have this very unique way of bonding with this metallic sea, this gives rise to most of the properties that we know about metals. So we learned the properties of metals way back in Chapter 6 when we started talking about the periodic table in general. And one of the things that we said was that metals conduct electricity. And then we sort of just made that statement and stopped. When we talked about ionic compounds, we talked a little bit about what is necessary for a atom, for a particle, for a solution to conduct electricity. And we said that they need to have two things: charged particles, free to move. In ionic compounds, when they're dissolved in water, it's the ions themselves are the charged particles that free to move. In a metal, the charged particles are, in fact, the actual valence electrons, right? And this picture here is showing us that these free electrons, these delocalized electrons in the electron sea, are able to sort of orbit one atom, go on to another atom, and so we would have a movement of current, a movement of electrical charge or negative charge. And that is what electricity is. So as the electrons are able to move through, then that's what electricity is. So that's why metals can conduct electricity. Some other properties of metals that we talked about is that they are malleable and ductile. So this picture over here shows a little bit about, what is going on when we do try and change the shape of a metal. And so here's the force, think of this as like the world's tiniest hammer, right? So there's the little hammer moving down. And when it distorts that sort of piece, because there's no rigid structure to where these electrons in the electron sea are, you can easily move them around and it just sort of distorts it. But you're never going to set up a situation where there are negative ions next to negative ions or positive ions next to positive ions like there are in an ionic compound. Remember, we said ionic compounds were brittle, that they would shatter. Metallic compounds or metals are malleable. One way to sort of understand how this works is think about sort of a particulate diagram of a metal. When you think about what's going on with a metal, kind of think about like macaroni and cheese. So if you're thinking like Panera mac and cheese, think of the noodles themselves as those metal cations. So the nucleus and all of its core electrons, and they are held together by that like ooey gooey cheese, which in this case would be like the electron sea. And even though it does hold it together, it doesn't hold it together in any particular shape, that the shape can be distorted and you can put it into another bowl and you can put it on a plate and it will change shape, but it still sort of holds together. That's what's going on with a metal. And finally, we talked about how metals have high melting and boiling points. And I think we said relatively high because some of them don't, right? Mercury is a liquid at room temperature. We could see lithium has a melting point of 181 degrees Celsius. That's not really all that hot of a temperature. But then we get to, copper and it takes an awful lot of energy. And if you think about, why that is, if we go back to thinking about, this model of what a metal is, if I was to boil this, if I was to absolutely break this up into individual atoms, I would need to overcome the attraction between the negative electrons and the positive metal ion. Anytime that I'm overcoming a really strong attraction like that, it's going to take an awful lot of energy. And then finally, what is an alloy? An alloy is sort of a special group of metals that is, sort of, as I was saying earlier, is this a mixture or is it a compound? Well, so what an alloy is it's, we do call it a mixture of two elements where at least one is a metal. It's oftentimes two metals, but it can be a metal and a non-metal as well. And the alloys are made to give very specific properties. And although you have probably heard about alloys before, because actually very rarely do you see examples of a pure metal. Most metals that we see around us are alloys of different metals together. Anytime that you see gold, you can see here 14 karat gold. Well, gold itself, if it was pure gold, the melting point of pure gold and the malleability of pure gold make it really too soft to have any use, especially in jewelry. If you had a ring made out of pure gold, as soon as you bumped your hand against something, you would dent the ring, right? You could easily take a pure gold ring and just go and smush it right in half. So that really wouldn't be useful. So what we do is we add another element to it. In this case, with 14 karat gold or 12 karat gold or 8 karat gold or 18 karat gold, we will often add silver, sometimes copper. That's how we get pink gold, is we add some copper atoms in there. And what that does is that makes the alloy stronger. If the two atoms that we're mixing together are of around similar size, we would call that a substitutional alloy, because one atom just kind of substitutes for another atom. And is this a compound or not? Well, if the other atom that's in there is gold, then is there metallic bonding going on? Yes. And bonding says that it would be a compound. Is it a very specific ratio? Well, no. Like, we could have a lot of silver mixed in or a little silver mixed in. And when there's not a specific ratio, that tells us that it's a mixture. So this can sort of be thought of as it doesn't really fit the definitions perfectly. The other type of alloy that there is, instead of substitutional, is interstitial. The word interstitial means like in between. And in interstitial alloy, you can see steel is the biggest example of that. In steel, we actually put atoms of copper inside the iron, and it sort of goes and fills the holes. If you notice that all of these iron atoms are in this nice rigid geometric pattern, but then there's spaces in between those iron atoms. If we fill those with a much smaller element like carbon, what that will do is that will vastly increase the strength of that metal. So iron by itself is relatively strong, but then when we add iron and carbon and have steel, that is much stronger. This table is just for reference. You don't need to memorize anything for it, but if you take a look, these are some common alloys, and these are actually, substances that you probably have used a lot. If you think of like brass, so yellow brass, that's what all those instruments that are made of, musical instruments that are made of, mostly copper with a little bit of zinc. The zinc is in there for a number of reasons, but one of the main reasons is that it helps the copper not react with moisture as much, right? If you're playing a musical instrument and the air that you're blowing through actually has a much greater water content than just the ambient air around us. And over time, copper would form that green patina or outer coating like we see on the Statue of Liberty. If we add some zinc to that, it can cut down on that. Bronze, right? This is the third place medal in the Olympics. So that is copper with a little bit of tin. And again, chemically stable in dry air. That makes it so that that copper does not react with the air as much. Stainless steel is that iron with a little bit of copper, but actually with a decent amount of chromium in there. And that really helps it resist corrosion, because iron, as we know, readily reacts with the oxygen in the air to form rust, right? Iron oxide. But we use stainless steel for cooking. We use it for medical instruments. You use it for like earrings and jewelry sometimes. Sterling silver is another one that, just silver does tarnish in the air, and adding a little bit of copper to that helps prevent that from happening. Dental amalgam. So this is what a silver filling is made out of. And you can see it's mostly silver, but there is a little bit of some other elements, including mercury. And that can be, some people don't like to have the silver fillings because there is mercury in them, but there is little to no evidence that mercury ever makes it into your body to have a negative effect. So anyways, these are just some interesting information about some alloys, but the big thing that you need to know about metals is about their bonding and really understanding what's going on in this electron sea and how that leads to all the different properties of metals like malleability, ductility, and how it conducts electricity.